other rates of change part, we did, or rather, I believe I did talk about. Yes. Oh, you need it. Sorry, Emma. Yep. I believe I talked about this Friday, but I'll recap, and then I apologize if I'm misremembering and I didn't talk about it. But I did talk about, or I believe I talked about how the slope of a line, so the slope of a tangent line is a rate of change in Algebra 1. When you learn about slope, you also learn about rates of change. You see that they're calculated the same way. It's a change in y over a change in x. So slope is a rate of change, meaning the slope of a tangent line is a rate of change. We talk about it as an instantaneous rate of change, as a rate of change at a specific point. And then velocity is also a rate of change. It's the change in position, so displacement over the change in time. And then instantaneous velocity would be at a specific time, not over a time interval. So then because slopes of tangent lines and instantaneous velocities, because they're both instantaneous rates of change, they're calculated using that same limit, or those two same limits we've been talking about. And that limit actually can help you find any instantaneous rate of change. So slope of a tangent line is one application, instantaneous velocity is one application, but anything that's described as a rate of change or an instantaneous rate of change can be calculated using that limit. So this is saying here, suppose you have, this is just some general function, so suppose y is a function of x, so y is f of x. And then we have, if x changes from x sub 1 to x sub 2, then the change in x, also called the increment of x, we can represent as delta x. But that change in x would be x sub 2 minus x sub 1. And then the corresponding change in y, so y is the function evaluated at those x values. The change in y we could represent with delta y, but that would be the function evaluated at x sub 2, so f of x sub 2 minus f of x sub 1. And then you might hear the phrase or terms difference quotient.
I only got one of the two.
This was from Friday.
Okay. Well,
Were you here Friday?
I don't remember.
I don't know that I have another extra one, so you must have been here Friday. Yeah, I don't have another one, Connor, sorry, but I think you were here, so your sheet is probably somewhere. All right, so you might hear difference quotient come up, but the difference quotient, which is the average rate of change of y with respect to x over the interval from x sub 1 to x sub 2, would be just your change in y over change in x. So how rate of change is defined, so that would be how we defined change in y and change in x above, f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1 is how that would be calculated. And then with an average rate of change, as we've seen with the slopes of secant lines and then average velocities, if we let x sub 2 approach x sub 1, so as x sub 2 would get closer to x sub 1, then this difference, change in x, would become smaller and smaller. It would approach 0. And the limit of these average rates of change is called the instantaneous rate of change of y with respect to x. And I have instantaneous in parentheses. If they just ask you to find rate of change, that's implied instantaneous rate of change. Otherwise, if it's average rate of change, it will say average in front of it. But the instantaneous rate of change of y with respect to x at the x value x sub 1 would be, and I'll write it a couple different ways here. It could be written as the limit as the change in x, delta x, would approach 0, and then that would be of your delta y over delta x. but this could also be written as the limit as x sub 2 approaches x sub 1 of f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. And I wrote these how they're presented because this is a more general form, but what I want you to realize is that both of these limits are the exact same limits we've been working with. If I let x sub 2, if I let x sub 1 be a, for example, and then x sub 2 be a plus h, notice then I have f of a plus h minus f of a over, and this would be a plus h minus a, so this would just be h, and therefore this would be as h approaches 0. So it's that same limit that we've been working with, and that limit can help you find any instantaneous rate of change. Questions on that? Okay, so then example 2 is actually an example where we are not using this limit, but it is still asking for a rate of change. From the practice on here, 23 parts A and B, and then 25. So these, while they are using or could be using that same limit we've been working with, we're just talking about other rates of change. You can now take a look at those if you didn't already. But in example 2, here we have temperature readings T in degrees Celsius are recorded every hour starting at midnight on a day in April in Whitefish, Montana. The time X is measured in hours from midnight, and the data are given in the table below. So this is a case where we do not have an actual equation for the function T. We are just given the table. So how you work through this, you've done this type of problem already, but perhaps it hasn't been worded in this way. So part A says find the average rate of change of temperature with respect to time for these times here. So from noon to 3, noon to 2, noon to 1. So average rate of change is just going to be your change in temperature over your change in hours, which would be change in X in this case. So looking at our table, what is the temperature at noon? Yeah, so that would mean X is hours from midnight. That would mean your X value is 12, so 14.3. And then at 3 p.m., your X value would be 15. So that temperature would be 18.2. So we would have a change in temperature of 18.2 minus 14.3 all over the change in X. You could just put 3 hours right away, or if you wanted to use the actual values from the table, it would be 15 minus 12, which would be 3. So this would be 3.9 divided by 3, so 1.3 would be the average rate of change from noon to 3 p.m. What would the units on that average rate of change be? Degrees Celsius per hour. Okay, so then that same calculation would happen for the next two parts, noon to 2 p.m., noon to 1 p.m. So we already know at noon it's 14.3. At 2 p.m., so that X value would be 14. That temperature was 17.3. So we would have 17.3 minus 14.3 over 14 minus 2. So that would be 3 divided by 2, so, 12, sorry. I was thinking 2 in my head was the actual difference there. And then, so that would be 1.5. And then from noon to 1 p.m., So 1 p.m. would be the x value 13, and that temperature was 16.0. Oops, this would be 13 minus 12, it's just a difference of 1 hour. So really it's just that difference in temperatures, and that would be 1.7 degrees Celsius per hour. So those are all average rates of change. You are asked, there are AP questions that will just ask you free response and multiple choice that will ask you for an average rate of change. So just understanding that's just finding change in y over change in x, whatever those values represent. And then for part B, it says estimate the instantaneous rate of change at noon. Now this might be a little deceiving because this was asking you over shorter and shorter time intervals as your time approached noon. But there really isn't a clear limiting value here from your average rates of change. So when you have a table, how would you find an instantaneous rate of change? Because you've done this before. Ava? Yes. So we would take, if we're focusing around noon, that's when x is 12. You can take the value at 11 a.m., so when x is 11, and then the value at 1, and find the average rate of change between those two, and that would be the closest approximation. Or that is the same as finding the average rate of change between 11 and 12, and 12 and 13, and then averaging those rates of change. So instantaneous, the best approximation we can get from the table would be 3.9 divided by 2, so 1.95 degrees Celsius per hour. And this is what they would want to see. If you have a table on the AP test and they asked you for an instantaneous rate of change, this is what they want to see in your work. They want to see that you're actually using the values from the table, and then they want to see your answer here. So that's the closest approximation they're looking for. They're not looking for you to find a regression for this function in this case. That's what they want to see. That's the best approximation we can get. Are there questions on that? Okay, but again, to point out, this is a problem that you've done before, and now it's asked again. It just might be asked in a different way. So anytime you're finding an instantaneous rate of change from a table, that's the method that you use, whatever that rate of change represents. All right, we can then move ahead to officially define what a derivative is. I'm glad you are all very excited about this. Thanks, Jake. All right, differential calculus, one huge branch of calculus, study of derivatives. So a derivative is defined using a limit, which is why we just spent the last 6 sections of Chapter 2 learning about limits. Starting off right away with the definition of the derivative. So the limit we've worked with, we've just seen that this limit represents slope of a tangent line. It represents instantaneous velocity. It represents, in general, any instantaneous rate of change, which then is defined to be what a derivative represents. So the derivative of a function f at a number a is, and with this notation, it looks like f, and then it looks like a, well, it's not a 1, apostrophe, thank you. It looks like an apostrophe, but this is read as f prime of a. F prime of a is how that is read, but it means the derivative of f at a. A is an x value, like we worked with before. So the derivative of a function at a number a, f prime of a, is the limit that we've been working with, limit as h approaches 0, of f of a plus h minus f of a all over h, if the limit exists. And then this was not the first limit we learned. We had first learned this limit down here. So another way of stating that definition, f prime of a can also be found by finding the limit as x approaches a of f of x minus f of a over x minus a. Maybe you want to make a note to yourself, understanding what a derivative represents, and really we talk about it in this section, but because we just talked about how this limit represents any instantaneous rate of change, now knowing it's a derivative, I would maybe include on your notes a derivative is an instantaneous rate of change. Meaning anytime you are asked to find an instantaneous rate of change, you find the derivative. Yep, one application would be the slope of the tangent line. All right, so for example 1, it just says find the derivative of the function f of x equals x squared minus 8x plus 9 at the number a. So that just means using one of these two limits, you are finding that limit. Any preference? With h, without h? With h, I heard first. So f prime of a will equal, I'm just going to write down the formula first so I have it all on the same screen here. That way I can move this up. Okay, so this is just the definition of what f prime of a is equal to, the limit that we've been working with. So then I'll have the limit as h approaches 0 of, and then remember f of a plus h, this is your function f of x evaluated at a plus h. So all of the x's are replaced with a plus h. So we have, instead of x squared, it would be the quantity a plus h squared minus 8 times the quantity a plus h plus 9. So that whole thing would just be f of a plus h. And then minus f of a is your function evaluated, all of the x's are a's, and I'm going to put a parentheses because I'm subtracting that entire quantity. So I'd be subtracting the quantity a squared minus 8a plus 9. And that's all over h. And then we simplify the numerator. So how I talked about on Friday as well with finding your slope of your tangent line or finding your instantaneous velocity and keeping a as a first was kind of leading into this here where you're finding the derivative at a. So the quantity a plus h squared would be a squared plus 2ah plus h squared. And then I can distribute this minus 8, so minus 8a minus 8h. I still have plus 9. And then I can distribute my subtraction to that quantity, so minus a squared plus 8a minus 9 all over h. And if we did the algebra correctly, everything without an h on the top should cancel out. So I do see I have a positive a squared and a minus a squared. I have a minus 8a and a plus 8a. And I have a plus 9 and a minus 9. So then I'm going to rewrite this, but everything I'm left with on the top has an h, so I'll factor that out right away. If I factor out an h, I have 2a plus h, and then don't forget about this minus 8h that's in the middle here. So I would still have the minus 8. That's all over h. The h's then cancel out, and that means that I can now substitute in 0 for any remaining h's. And this means I'm going to go back and actually write the f prime of a in front of it. So f prime of a is equal to, if I replace h with 0, I still have 2a minus 8. Yep. Yes, and it's important for you to understand that this is the exact same thing. It has a different meaning, so you need to understand that what we did Friday, and even what we did, when did we do slopes of tangent lines? Wednesday. This limit, it's the exact same limit. So we went from slope of a tangent line to instantaneous velocity, they're the same. Then any instantaneous rate of change is the same limit, and now the derivative is the same limit. So the derivative is any instantaneous rate of change. The questions are just asked differently. So I've said this before, I could ask you 5 different questions, and they could all be the exact same process. But you need to understand that they're all the same process. So then this next part is one way to interpret the derivative, as we've already been talking about. So we know that this limit is the exact same limit, or rather these two limits are the exact same limits we use to find the slope of a tangent line. So that means we can say the tangent line to y equals f of x, so any curve at the point a, f of a, is the line through a, f of a, whose slope is equal to f prime of a, the derivative of f at a. So the slope of a tangent line is the derivative. That is really the geometric or the graphical representation of a derivative, is the slope of a curve at a point. The slope of the tangent line, or the slope of the curve. So all this is showing below here, it's showing the 2 different limits that we've used to find slopes of tangent lines, which are the 2 different limits that you can use to define the derivative. And they're just showing the different representations. So we have our tangent line through the point P. And so the one is just showing that if you let your x values go from a to a plus h, it's showing your change in y, and then your change in x is just h. And your slope of your tangent line is the limit as h approaches 0, versus the other limit is if you go from the x value a to just x, then your change in y is f of x minus f of a, your change in x is x minus a, and your limit is as x approaches a. So it's just showing, I guess, the limits we've been talking about already. That's all that's there to show you. So I included on the back at the top, if we use the point slope form of the equation of a line. So this shouldn't be anything you're memorizing, it's just when you're writing the equation of a tangent line. We can write the equation of a tangent line to the curve y equals f of x at the point a, f of a. This would be the point slope form. So all that's in place of your slope m is f prime of a. So it's just making you realize the slope of the tangent line is the derivative of f at a. And then the f of a, just realize that's your y value at your point, a is your x value at your point. What this is showing here, I've showed you this before, sometimes they just add this f of a to the other side and write it that way, so it's not technically point slope form, but you might see equations just left written in this form. But again, the f prime of a is your slope. So not a formula that you should have to memorize if you already know point slope form. So then in example 2, this is tying into example 1. It says find an equation of a tangent line to the parabola y equals x squared minus 8x plus 9. This is the same function. So same f of x as example 1. So find the equation of the tangent line to that parabola at the point 3, -6. So why I'm pointing out that it's the same function is now when you're finding the equation of a tangent line, you still need your slope first. Your slope is equal to the derivative at a, and we found f prime of a in example 1 for that function. So f prime of a for that function was 2a minus 8. But if this was an example where you were starting fresh, you would need to find that derivative first. So that means, what's our a value in this problem? 3, the x value of your point. So our slope is going to be f prime of 3, which is 2 times 3 minus 8. So 6 minus 8, -2 would be our slope. So once you've found your derivative, you substitute in your a value to get your slope. Now we have our slope is -2, our point is 3, -6, and we can write the equation of the line. So if I use point slope form, I would have y minus -6, so y plus 6 equals -2 times the quantity x minus 3. And it is fine if you just leave it like that. Yes. Yeah, because this would be y plus 6 equals -2x plus 6, subtract 6, so y equals -2x. Yeah, so you can rewrite it in the slope-intercept form. You don't have to leave it in point slope, but you can, is the point. Okay, any questions? So really, you've had these problems already. Find the equation of a tangent line to a curve at a point. You're going to see more practice with that, knowing that the derivative is the slope. It's kind of just tying those two different ideas together, having you connect those ideas, I should say. In example 3, I'm going to have you, for sure, with the time we have left, work on part 1 of this in your groups. So it's giving you a graph of some function f of x below, and you can see on the curve we have points P, Q, and R at the x values A, B, and C. And it says, place the following quantities in order from lowest to highest. And it gives you f prime of A. So you have to think about what does f prime of A represent on the graph. F prime of B, what does that represent on the graph? The slope of PQ, so the slope of line PQ. The slope of the secant line QR, and then f of c minus f of a over c minus a. Again, you have to think about what this means on the graph. So you're placing those 5 quantities in order from lowest to highest. When it says make sure to give justification, I'm not looking, I mean, you can on your paper, because this is for your reference to look back at. You can write out how you came up with it, but just making sure you would know how to explain or how to justify why you put them in the order that you did. Well, you are looking at the graph, so like if I asked you to explain why is, f prime of A the largest, you should be able to explain why that is what I'm saying. All right, so work on at least number 1. I'll kind of come around if your group has it. Then I'll explain what to do in number 2 because it's worded kind of weird.